Bismillahirrahmanirrahim. Greetings. Abstract algebra, also known as modern algebra, is a branch in mathematics, as we all know about. In this video lecture, I'm going to give you an overall picture of what abstract algebra is all about and why it is also labeled as so. And I also intend to upload more videos about this subject, and I will be kind of selective so that the summation of all of them will be sufficient for a first semester undergraduate course in abstract algebra. Now, in order to better comprehend the subject, I begin with very elementary arithmetic, the difference between arithmetic and algebra, and then I go to the difference between algebra, high school algebra, and abstract algebra that usually we take it in college. Okay, then let's start, shall we? In our early mathematical endeavor, we first learn how to count numbers, is that right? Natural numbers. 1, 2, 3, 4, and so on and so forth. And then we learn how to add and subtract them. And usually our tutors or our teachers use tally marks or marbles, beads, or similar thing to demonstrate the idea for us. And then we are tested with something that I'm going to put it on the bulletin board. That, for example, 9 plus 7 equals to blank, and we are supposed to fill up the blank. Or 9 minus 7 equals to blank, and we are supposed to fill up the blank. They are kind of typical question that we are being asked. Also, the calculator nowadays has become a toy in reality. The one that functions as addition, subtraction, multiplication, division. You can buy them for about $1 in Dollar Tree. So the kids are playing with them, and there are bottom the key for addition and for equality. So you give them number, then you add the addition, then you say equal, and he gives you the answer. And even kindergartens, late kindergarten, early grade school, they can play with them. And I'm going, as a matter of fact, to come back for these two keys that I mentioned, the addition key and equality key. So how they play important role in abstract algebra. Okay, now let me put this one up, if I may. Notice that here, Notice that here 9 plus 7 blank, we fill it up, is that right? And then at this stage of maturity for the kid, if we give them 7 plus blank equals to 2, the kid kind of hesitate because it's different than what he has learned in his small logic. So he has learned that if you add two numbers, the result, the summation will be bigger than either of the two. And here you're adding something to 7 and the result is less than 7. So it's kind of, he hesitates and look at you. And then even the keys of the calculator that he has in his hand and he played with them cannot help him to answer this question. Do you follow me? Okay. The former two examples, 9 plus 7 is equal to blank and 9 minus 7 equal to blank, are examples of arithmetic. It's straightforward. The latter one that needs more information, needs manipulation in order we simplify and reach it in in that stage, so that we could use the bottom or the keys of the calculator. This is example of algebra. So algebra needs manipulation. In this case, we have to both add to both sides -7. I'm coming to that, and the kid is not already exposed to the negative integers, so he doesn't know and he couldn't solve that. Okay, now let's go and see what will be the difference between algebra. By algebra I mean high school algebra and abstract algebra. Now I have the same question, I put it up, but for the junior high school student that I will be asking this question. Now let me see how the student may answer. I said solve this one to a junior high. The blank noise is indeterminate. X has replaced the blank that we would like to value the value of the determinant value of that. Now here we ask in the set of positive and negative integer, I mean the union of them, and or in the set of natural number and their negative union of them, solve this one, I asked the junior high. So the student goes and he says, we add to both sides -7. Stop. Why did you select -7 to add to both sides, I ask. The student answered, because -7 and 7, they cancel each other. What do you mean by cancel each other, I ask. Cancel each other out, what do you mean? I don't understand, can you be more explicit? Can you tell me what you mean by cancelling out? Well, when you put -7 and 7, you get 0. So then we find out what is x. Yeah, but the set that I gave to you, I'm saying to the student, did not have 0 in there. I said positive integer and negative integer. There was no 0. If there is no 0, so when you add -7 to 7, what do you get? So the additive inverse of 7 is not -7 if 0 is not there. Do you follow me? Now, let's make another example just for the sake of it, for again a junior high student, how they work on it. Usually, now, suppose I ask the same student this question, solve it for x. So the student says, I multiply both sides by 3/2. Then I ask again similar, why did you select 3/2? Because 3/2 and 2/3, they cancel each other out. Again, I ask them question, what do you mean cancel out? I don't know, I just want x by itself. Can you please be more explicit? I don't know what you mean by x by itself. Well, I want x by itself, I don't want anything in front of it. Do you follow me? Again, I don't understand, would you be more explicit? So I give her a hint. Do you mean that in front of it you want to be 1? Yes, that's what I mean. Because 2/3 and 3/2 are multiplicative inverse of each other. No, my point of saying that is that the students are mechanical. They are kind of recipe following. That's the way they have learned mathematics, unfortunately, and that's the way some teachers teach us, unfortunately. So that is in fact one of the cause of the so-called anxiety in mathematics, because the critical thinking is absent, because there is no demand for justification. And that's what, when they come to upper level courses in college, they usually face difficulties. Okay, now let's go back to the first one, which is extremely primitive question, is for the grade school or kindergarten, and see how the abstract algebra looks at that. Let me put this one here. Now, abstract algebra put the very same question that the students are taking for granted, again mechanical, they solve it. He puts it under magnifying glass. He looks at it through the eye of the eagle, the bird of the prey. and try to extract information out of that, and that information leads to definition. Definition leads to kind of conjectures. Conjectures, we prove them, leads to theorem, and by doing those stuff, he makes a system, and in the frame of that system, he demands justification. That's what abstract algebra does. Now let's see how he extracts information from that leads to the definition that we are going to talk about. First, you notice that we are doing with numbers, is that right? So we start with the set of natural numbers first. Set. Then we add to that the negative natural numbers. Set. Now the set is increased. So he's dealing with sets. Sets of what? Sets of numbers. Numbers, different, the numbers in a set, they belong to different sets. We have set of positive integer, negative integer, non-positive integer, non-negative integer. Then we have set of rational number, we have set of irrational number, we have set of real numbers, we have set of complex numbers, and it goes up further. As a matter of fact, when you go upper level mathematics, there are other kind of numbers. But of course, it's outside this subject. Now, then after he knows that he's dealing with sets, then he pick up on the operation of addition. What is addition? Addition is a function. It has input, it has output. The input are two things. That's what is called binary operation. So you give him two things, he gives you a unique things out. The uniqueness is very important in mathematics. So you give unique things up. That's what is called binary operation. Now, because the set, if you notice that the set that I put should be closed under what? Under the operation. Now, I took the 0 away from the set of integers, and then the set was not closed. Because when you take two elements, like 7 and minus 7, you add them, you get 0, but 0 is not there. So we demand that the operation, the function, the binary operation be what? Causes that the set to be closed. Which means any two elements in the set you get with respect to the operation, the result of that must be an element in that set. Set. Alright? So right now we have a set together with the binary operation. Then you ask this question, you say, okay, if it is binary operation, then what are you going to do if you have 3 numbers or 4 numbers you want to add? As a matter of fact, that's a good question to ask, because no one can add 2 plus 3 plus 4 one time. Impossible, think about it. So what you are so used to it, on your subconscious, it comes so quickly that you don't even realize that you are taking 2 at a time. So first you add 2, 3, 4, you add 2 and 3, you get 5, you add 5 to 4, you get 9, or you add 3 and 4, you get 7, and you add 7 plus 2, you get 9. That's what you get 2 at a time, because the machine cannot work with more than 2 or less than 2. If you say 1 and you push the key of the calculator, it gives you nothing. You have to give him the second number in order to give you the result. Then you add the result to another one again, and you can keep continuing that for as many times as you wish. Alright? So we demand that our addition, in this case operation, to be what? To be associative, which means doesn't matter which 2 you are taking. Now, the reason I brought that one up, because subtraction is also binary operation. You have to give him 2 things in order to give you what the result of. Now, the difference is that if you give 3 things or more, then if you don't specify which 2 you are taking first, 2 different people can get 2 different answers. So we say subtraction is not what? Is not associative. So we impose the associativity in there. Then you say, okay, if this is the case, then I cannot work anymore with subtraction. Subtraction is causing problem, but subtraction is here. The matter of fact is that the addition does include subtraction as well. The binary operation of addition is kind of, you can say, implied. The subtraction is implied because subtraction is addition of a negative number. Do you follow me? So subtraction, again one more time, is a binary operation, is not associative, so we don't consider that because it will create kind of a problem. And mathematics is very meticulous and very precise subject. When there is something that is causing difficulty, they filter it out by giving definition or giving a name, in this case associativity. So we have a set and we have an operation in that. Then equality. The students, we have a key in the calculator, so has some kind of function. Then we don't even think about it. Add to both sides. You ask a student, what does equality mean? She or he look at you, I don't know, equality means equality. What do you mean equality is equality? It means two things are equal. You see, the kind of justification and critical thinking is absent. Even for equality, they are taking everything for granted. Now, equality in abstract algebra is a relation. And that relation is called, has the property of reflexive commutativity and transitivity. So it partitions the set into equivalent classes. So when I upload more videos, of course I will be going through them more in detail, but this is just overall picture. So what does that mean? That is the property of equality, that under magnifying glass, the abstract algebra notices it and takes that information out of it. So far what do we have? We have a set, we have a binary operation imposed on the elements of that set. Then what? That set must be closed under the operation. That's one thing. Second one, the set must contain an element that we call it identity. For addition is 0, because any number plus 0, the identity of that number is not changed. 7 plus 0 or 0 plus 7 remains 7. Nothing is, nothing altered that. Alright? So here, addition is what? Again, is operation that we are doing that. We have a set, we have a operation imposed on that, and we know more already so much about the operation. So the identity of the operation must be in the set. And also, any elements of the set that you take, in this case addition, the additive inverse of that number or that element must also be in that set. Do you follow me? So if 7 is in the set, negative 7 also be in the set, that negative 7 plus 7 will produce the identity 0. So the additive inverse is defined with respect to the identity element in the set. So first we talk about identity element before we talk about which two elements are inverse of one another. Alright? So far so good. Now then what happened in abstract algebra, more and more the definitions come. Of course we start with few axioms first. And then definition leads for more and more theorems. And then there is need for vocabulary, new vocabularies, new terminologies. And their symbolism come, ocean of symbolism. So they expand and expand and expand to the extent that you lose the sight of the forest because of the trees, because of so many trees. But the matter of fact is that without trees, there is no forest. So those trees that they are there and give a student difficulty in abstract algebra, they are necessary to be there. It's not that they are trying to give a student hard time. Are you with me so far? So you have to kind of adjust yourself to that many trees in the forest. Okay, now the other thing is that the abstract algebra also, after he gave us the conceptual understanding of the subject through the numbers, because we are familiar with them, and demand justification, after we become skillful about that, we take a couple of weeks, and then the elements of the set that abstract algebra works with are no longer numbers. Isn't that fascinating? So he deals with objects that they are not numbers, but the definition that we are going to call is named as a group is applied to them, and algebraic manipulation is also applied to those objects, and expands so much that has applications so much outside the mathematics. Now, for instance, computer science is really based on that. If you are going to go for PhD computer science, you must know abstract algebra real well. And so, for example, chemistry and like I said, geology, mechanical engineering, electrical engineering, anything that related has structure, abstract algebra gets into that. I'm going to talk to that shortly. Okay, now I think we know what abstract algebra is, has expanded so much that the high school algebra becomes like a little lake connected to what? To the ocean of abstract algebra. Now, let's go back to the question that I started with, and that is why it is also labeled as modern algebra. One reason is that the algebra that we are used to, we call it high school algebra, has thousands of years of history. We can trace it back to ancient Greeks and Babylonian and so on and so forth, for thousands of years. Whereas abstract algebra is kind of new, it's only a couple hundred years old. It starts from Cauchy and then goes to Abel, then goes to Galois. Has a very beautiful history of those mathematicians that really, they are father of this subject, they developed it. All right? That is one reason it's called modern. Second one is that, as I already mentioned, he deals with the set of objects that they are no longer numbers. I will make some example. All right? He deals with them, and that is another reason they call it modern algebra. And let me make an example about this one. Like let's say table, Mendeleev table in chemistry that we are used to it. The elements that they have same structure, they can, abstract algebra can go and define some kind of function that relate them together and say, okay, this element and this element, they have same structure. So based on algebraic structure, I'm going to go over that, the periodic table maybe can be rearranged algebraically. Based on what? Based on, they call it isomorphism. Alright? So what it does, the other thing that modern algebra does, he goes through the structure of the thing. And by doing that, he defines a function and two things that they are absolutely look at the first glance different, we end up to have what? To have same structure. So you study about that. Anything that has a structure, I already mentioned, the chemistry, like botany, like chemical engineering, like geology, anything that concerns with the structure, abstract mathematics can go into that and explain it what? Algebraically. Alright? So that's what is called modern algebra. Now, it's like, let me make another kind of analogy or metaphor or something like that. Suppose you have something floating on the top of the water in ocean, and you have something which is on the bottom of the ocean that you have no access to that. But you can make a function that relate these together and see that these two they have same structure. So by knowing the thing floating on the top of the water in the ocean, you know so much about the thing which is on the bottom of the ocean that you have no access to touch or work on it. Do you follow me? So again, these all are coming from abstract algebra. Then a structure that, again, I repeat myself, isomorphism they call, that they relate them together, plays very, very important role in abstract algebra that expands and goes to outside mathematics, in a sense, in science. Also, the other thing it does, some of the branches of mathematics, abstract algebra unites them together. And again, we will see them. I will make some, tape comments. I will go to some geometry and see how they have same kind of group. So, okay, then let me make a formal definition about group. Then I have written already, I put it on, but in the internet, in a flash of, time, you can always find the definition of group over there. So what is group? The definition, which is very fundamental, very important in abstract algebra, and that is a set along with or together with a binary operation, such that the set is closed under that binary operation, and then the identity with respect to the operation is in that set, is an element in that set, and for any element in that set, let's x, the inverse of that with respect to the operation must also be in that set. So the collection of all of them is definition of group. One more time, I emphasize that group is fundamental and very, very important first definition in abstract algebra, in modern algebra. Okay, then I have this one, I hang it up for you, and then I go ahead and zoom it at the end before I close it, if you like to write it. And also, until more coming videos, I wish you all prosperity. And also, I encourage you to watch my other videos, because I teach a little bit different, in a sense that I go into the deep of the subject and I demand justification. And I try to develop the idea from scratch with my student together. Alright then, I hope that you benefit from my videos, and until more coming, I wish you all prosperity. So let me hang it up, then I say so long and goodbye to you. Okay, then I zoom it back, and again for the third time, so long and have a prosperous and happy life.